Hi, my name is Aaron Kang, and I'm a structural engineering major set to graduate in 2026 from UCSD. This summer, I worked on tailoring the viscoelastic properties of graphene oxide thin films through controlled processing techniques. I was part of the Tehrani group with Professor Mehran Tehrani as my PI. So, a little introduction to the material I'm working with, graphene oxide. So, graphene oxide is a novel nanomaterial containing oxygen functional groups attached to hexagonal carbon lattices in crystalline form. Research has shown that graphene oxide, or GO, has excellent mechanical and electrical properties compared to other materials. My research this summer involved exploring the viscoelastic properties of graphene oxide, which is a property given relatively less attention in this field. Specifically, I fabricated 6 different samples of graphene oxide thin films and measured their damping properties via dynamic mechanical analysis. So I began with a diluted 10 mg per milliliter precursor solution with dispersed graphene oxide flakes and centrifuged at 500 Gs to remove aggregated particles. I then filter pressed my dispersion multiple times to thoroughly filter out ionic impurities. At this point, the dispersion in liquid crystalline form, as observed in a capillary tube under an optical microscope, is also acidic, so I added a diluted 1 molar sodium hydroxide solution to deprotonate and neutralize those oxygen functional groups to reduce the GO surface charge density and electrostatic repulsion, allowing the GO flakes to come closer together. I then used a combination of superabsorbent polymer beads and evaporation via hot plate to concentrate the dispersion to 20 mg per milliliter or 2.8% to get an optimized domain size in the liquid crystal. After this process of tuning the dispersion concentration, I conducted shear-induced alignment via Doppler blading across a glass substrate. So that's basically sliding a metal box across the glass to spread out the GO dispersion, kind of like jam, to get what we call a wet film, and then it dries into a dry film over time. And then, this is where the varying processing parameters come in. I Doppler bladed a 200 micron wet film as the control film, a 400 micron wet film, a 600 micron wet film, a film that I dried in a drawer, a film that I dried in a fume hood, and a film that I stuck into a vacuum filter post-drying to covalently self-crosslink. Okay, so what do I mean by vacuum filter? So in this vacuum filtration setup for only that last film that I just mentioned, just that last film, the covalently cross-linked one, there's basically suction under the film that pulls it flat, and then I place a filter paper on top of the film, so the filter paper is effectively pulling vacuum on the film and essentially compressing it. So generally, these dry films end up to be around 10 microns thick, which is, fun fact, roughly the diameter of a red blood cell. So, I took all my samples and went over to the rheometer at the MRSEC facility on campus to do mainly dynamic mechanical analysis, but also some tension testing. On the TA Discovery HR30 rheometer, I used the tension geometry and loaded each film to 0.1 newtons, then oscillated from 0.1 micron to 20 micron amplitudes logarithmically in 5-second steps at 1 Hz frequency. What this cyclic loading does mechanically is that the hydrogen bonds between the interlayer oxygen functional groups are breaking and reforming as the pneumatically aligned geosheets are sheared against each other, causing energy dissipation and therefore damping. So this data that I collected from the TA Trio software and plotted via MATLAB, we have storage modulus, loss modulus, and tan delta of each film. You can consider storage modulus as the energy stored or stiffness, loss modulus as energy dissipation or damping, and then tan delta as the ratio between the loss modulus and storage modulus. From what we can see, increasing film thickness leads to increased stiffness, which makes sense, and the covalently cross-linked films have lower loss modulus and consequentially lower tan delta than the control film, which also makes sense because a mechanically compressed film, like I mentioned earlier, means that the GO layers are closer together and that there's less intercalated water molecules inside the film. I also conducted tensile testing on the films using the same tension geometry and collected their ultimate tensile strengths, as well as a stress strain curve of the control film, because I'm an engineer. So, geo has many potential applications, which is why it's such a novel nanomaterial. Geofibers can actually be used for smart textiles, energy devices, and actuators, while geomembranes can be used for water purification, gas separation, and selective permeation processes. For us, our lab, we can leverage and tune the intrinsic damping properties of graphene for vibration damping, noise reduction, and shock absorption. This translates into perhaps lighter and quieter aircraft and automobiles, or even something as simple as more efficient tennis rackets. So, according to this Ashby plot, admittedly, my films are not the best quality, but from observing the graduate students in my lab, it really comes down to a matter of skill in the fabrication process. This includes micropipetting, handling silicon dioxide wafers, dealing with filter press leaks, DMA loading, cutting samples, etc. I actually conducted my own mass loss study while fabricating these films, and in starting with 80 milligrams of precursor material, I lost about 35 milligrams in transfer, so there was definitely some technique improvements to be made. But I am still extremely thankful that I was able to learn how to do them in the first place. So I would like to thank our generous donor, General Atomics, for allowing me to have this opportunity to expand upon both my academic and hands-on experience in wet lab and research. I feel that I have found interest in this sort of research and dynamic-esque trial and error environment, and I will definitely want to pursue this dynamic in the future. And so I will end off with a quote here. As American author John Augustus Shedd once wrote, "A ship in harbor is safe, but that is not what ships are built for." Thank you.